to do this presentation about design constraints for wave energy commercialization. So some of you might be a bit sleepy after lunch, so I'm going to try to make this amusing. So first, why this title? So I'm going to introduce the title with a dialogue that I sometimes have with some of my non-marine energy friends. Okay. So when my friends ask me, what do? I say, okay, I work in marine energy, wave and tidal. And they tell me, okay, do you have machines out there? And I say, yeah, up north there are some machines, wave and tidal. And they say, oh, that's very cool. Are they producing energy? Are they commercial? And then I say, well, not really. Like, they are prototypes. They are being tested right now. So then the next question is like, okay, when are we going to get when are they going to be commercial? And then there's an awkward silence because I don't know that question, the answer to that question. So I wanted to have an answer to that question, or at least to avoid that awkward silence. And so where does the answer come from? So from the levelized cost of energy. Here there's a levelized cost of energy comparison of several technologies. And this is taken from a report from Carbon Trust in 2011. And as you can see, well, wave is around 180 pounds per megawatt hour. Tidal is around 80, and the other ones are lower. And I wanted to ask, actually, how many people think these figures are right? So if you could raise your hand, if you believe this is right, or right now we are around this cost. Okay, how many people believe it's not right? Okay, quite a few people. Okay, great. So yeah, I think the same. If these figures would be right, we will be at another stage right now. So what I wanted to, so how do we define, how do we know when we will be commercial? We need to look at these kind of figures. This is the LCOE cost reduction. Every report about marine energy has some kind of figure. You have the cost now, 20 to 60, don't know if that's right, and then we have a cost reduction until the target that is around 10, with a cumulative deployment on the x-axis. But I always think, like, is this, like, I see this all the time, is this right? So my question here is this science fact or science fiction? I see this all the time, so, and I don't see the cost reductions yet, so I want to know if this is right or this is not. So what are the questions I want to answer here? So what are the target costs for per cost center in order to achieve this commercialization? How can we translate these target costs to technical parameters, and which cost reductions are feasible and which cost reductions are not feasible, and then where the research efforts need to be focused. So the answer to this, we are going to do a reverse engineering exercise to see, basically, based on the target cost, what we have to do to achieve these target costs. So we are going to do a reverse engineering exercise. So what is reverse engineering? It's the process of extracting knowledge or design information from anything man-made and reproducing it, or reproducing anything based on extract information. So basically, it's doing the same so normally we have data, we analyze the data, we build a model, and then we make the decision. That's the normal design process for something. Reverse engineering is the opposite. We have a target, we have the decision, we know where we want to get, and then we redesign based on that target. So how do we apply this methodology to this case? So a normal assessment for wave energy converter, you design something, and then you see how much it produces, you check the cost, and then you see, oh, like, it's actually good compared to other technologies, or it's not good. Here, we are going to choose a different approach. We are going to select an LCOE target, then we are going to see how this LCOE target, how we assign thresholds for the cost centers, and how these cost center thresholds translate to technical parameters. And then we design something that fulfills all these conditions. So basically the questions are, what are these thresholds within the different cost centers for waste energy? So for the methodology, we are going to then select an LCOE target, then calculate the annual energy production based on some efficiency scenarios. Then from that, we will calculate the net present value of CAPEX and OPEX. Then we will apply some percentage for the different cost centers of the waste energy converters. We will identify then these thresholds for the expenditure within this cost center, and then we will translate these cost parameters to technical parameters, and then we will compare that with offshore wind. So I'm going to go through some of these steps to be a bit more clear. So we are going to have three scenarios depending on efficiency, average, minimum, and maximum, and we have 5 different types of WECs taken from a paper from Bavaria 2015, oscillating waste surge converter, oscillating water column, heavy end devices, oscillating waste surge converter floating, and then overtopping. So first step is selecting an LCOE target. We are going to select 15 pence as Wes suggested in a report last year. Then we are going to, so we have the LCOE equation there, we have the LCOE target, then we are going to define the annual energy production based on some capture with ratio taken from some historical devices from that paper, Bavaria 2015. We have the mean and a standard deviation of these 5 waste energy converters with some characteristic dimensions, so we produce a set of scenarios. Then once the scenarios once we have these, we can then we can apply percentage of CAPEX and OPEX values to this net present value of the CAPEX. So there has been lots of reports where there's a split of CAPEX. And actually, most of them are pretty similar. So the structure and prime mover is the highest one with around 30%. PTO is the second one, around 20-something%. Then connection, then foundation and moorings, and then installation. You can find many different figures, but most of them are more or less on the same page. Okay, and I'm going to show you some results. So. These are the expenditure thresholds per cost center for each of the categories that we developed. So we have 3 different scenarios, minimum, average, and maximum scenarios. So here we present 3 classes of converters. In the next slide there will be 2 more. As you can see, there's a big range of expenditure between minimum and maximum. There's a high difference between devices. For instance, there's for the oscillating water column, 1.2 million pounds. That means the money that you have available to spend in order to meet the target of 15 pence per kilowatt hour, and 700,000 pounds for heavy devices. So there's quite a big range there. In the next slide, we can see the other 2, oscillating waste surge converters and oscillating waste surge converters floating. As you can see here, the difference is even higher. For the floating devices, we have around 300,000 pounds to spend on the structure, while on the fixed, we have around $1 billion. That's quite a big difference. So if we put all this data together and we compare them on a chart, this is what we get. Well, clearly, higher expenditure is matched with higher capture efficiency. So the more energy you capture, then the more money you have to spend on your device. Here, the device with a higher capture is the fixed oscillating wave surge converter, and they have around 3 million per megawatt to spend. On the other side, we have the floating oscillating wave surge converters with a extremely low expenditure, around £1 million per megawatt. If you check offshore wind that I'm going to present is around 2.5 million per megawatt. So that is actually a very low value for anything offshore. What we wanted to check as well is, okay, this is great. We have the costs, the thresholds for the cost centers, but how do we translate that to technical parameters? And we thought that because the structure is actually the most important cost center right now, there's a lot of money put on just the structure of the device, so the mass is an important parameter. So we wanted to check the mass versus the rated power for existing converters. So we have translated the cost centers to this mass, so the blue and green lines, and then we have plotted some converters there. So don't worry if you don't know the converters, because we have pictures for all of them. So basically, we didn't want to classify converters. We didn't want to say you are doing it right or wrong. There's not right or wrong, but there's in this classification with respect how heavy your device is compared to your rated power. So there are some converters that are within the limits. So that means that with respect that cost center, they are doing pretty well. Then there are other converters that are actually this is in logarithmic scale, so the higher you are means the heavier you are, and the more money you have to spend on the structure. So in general, most of the existing converters are above the red line, so that means that they are pretty heavy and they are spending a lot of money on that. Just some comparisons with offshore wind. So these are some actual costs from some offshore wind technologies, all of them around 2.5 million. For the reverse LCOE, well, the only one that is around the same expenditure is the fixed oscillating wave short converter. The other ones are much lower. So the question is, can we actually achieve this cost? Can we actually achieve lower cost than offshore wind? So if we split that question per cost center, we can have, for instance, the PTO cost, all of them. So we have compared on the red line, high wind and wind float. They are two leading floating solutions. So for instance, for the PTO cost, all of them are lower than what the wind float and high wind have achieved. So that means that, yeah, it might be tricky, or the research efforts need to be focused there. On the other side, we have, for instance, mooring cost and installation cost. They are around the same order of magnitude as floating offshore wind. They are a bit bigger, larger than fixed offshore wind. And if we compare that with the structure and the mass, we can see that most of the converters are within the same order of magnitude of floating offshore wind, but they are one order of magnitude higher than standard offshore wind. So what we wanted to do with this is to see if which cost reductions are achievable and which not. So just let me finish with some conclusions. Clear link between the annual energy production and then the available expenditure you have. The fixed oscillating wave short converters have the higher efficiency, then have the higher available expenditure, and they are the only that have comparable costs with offshore wind. By breaking down the CAPEX, we see that there are some cost centers that have some targets that are very difficult to achieve, like PTO. Offshore wind has not achieved these limits with respect to CAPEX, so either they are difficult to achieve or we need to focus on that. And comparing the wave energy converters, we've showed that most of the existing prototypes have values that are one order of magnitude higher than the thresholds for technical parameters such as the mass. So I think, yeah, that's it from my side. Thank you very much for your attention.
This production is brought to you by the University of Edinburgh.